easier to drive, more safety features. In line with these requirements, automobiles continue to evolve by employing state-of-the-art technology, and Toyota is in the forefront of this trend. Power steering is just one example of this trend. Ease of steering from the low-speed to high-speed ranges is achieved through power steering. In this video, we will take a look at the power steering mechanism in some detail. We will discuss the following points: the principles of power steering, the operation of the vane pump, the operation of the control valve, power steering as a control device to improve driving feel, and finally, on-vehicle inspection of power steering. In vehicles without power steering, greater steering effort is required when the vehicle is stopped or moving at a low speed. Less steering effort is required as the vehicle's speed increases. Power steering enables the driver to use about the same effort to turn the steering wheel when the vehicle is stopped or moving at a low speed as when it is moving at higher speeds. Power steering is controlled by various mechanisms that reduce the steering effort required, while retaining the feeling of being in direct control of the vehicle, as with manual steering. Let's see now how power steering works, using a rack and pinion power steering system as an example. This is a simplified diagram of a manual rack and pinion steering system. For power steering, the following three components are added. First is the vane pump, which creates the hydraulic pressure used by the power steering system. Second is the power cylinder, a device that uses the flow of hydraulic fluid, that is the power steering fluid, from the vane pump to turn the front wheels. Last is the control valve, which regulates the direction and volume of the flow of power steering fluid to the power cylinder, in accordance with the movements of the steering wheel. Now let's use a simplified model to see how the fluid helps the driver turn the steering wheel. A constant volume of fluid is fed by the pump to the hydraulic circuit, which is equipped with a cylinder. Inside the cylinder is a piston. When valve B is closed, the hydraulic pressure inside the cylinder increases, pushing the piston up. When valve B is opened, the hydraulic pressure drops, decreasing the pressure on the piston, which then moves downward. In an actual vehicle, this piston is installed between the wheels of the vehicle. The piston assists steering by utilizing the flow of fluid, as we just explained. When the steering wheel is not being turned, the fluid returns from the control valve directly to the reservoir, without steering assist. The control valve operates when the steering wheel is turned, causing the fluid to flow into one side of the power cylinder or the other, moving the piston to the left or right. When the steering wheel is turned in the opposite direction, the control valve switches the direction of the flow of fluid, so the fluid flows into the opposite side of the power cylinder, moving the piston in the opposite direction. This is how the power steering fluid helps the driver turn the steering wheel with little effort. In a real car, the power cylinder and the control valve are incorporated into one unit in the steering gearbox. The vane pump is driven by the engine via a drive belt. Let's take a look at the construction and function of the vane pump and the control valve. The vane pump, driven by the engine, generates hydraulic pressure. A rotor is incorporated into the pump. This rotor rotates with the engine. When the engine is started, the vanes built into the grooves of the rotor move outward due to centrifugal force and are held against the inner surface of the pump. The pump is designed so that the space between the vanes and the inside surface of the pump changes as the pump rotates. This causes the amount of fluid discharged by the pump to also change in proportion to pump speed. Because the vane pump is driven by the engine, the volume of the fluid changes in accordance with engine speed. But what would happen if the fluid were sent to the power cylinder as is, without any control? Let's use the model again to do an experiment. Even if valve B is left open a certain constant amount, when the volume of the fluid from the pump is changed, the piston inside the cylinder rises or falls accordingly. This is because the hydraulic pressure inside the cylinder has changed. In the same way, the degree of steering assistance would change if the volume of the fluid sent out by the vane pump were to be changed by a change in engine RPM. To prevent this, the vane pump is equipped with a flow control valve which keeps the flow volume of the outgoing fluid constant, whether the engine is running at low or high RPMs. This flow control valve would correspond to valve A in the model shown previously. Now let's take a look at the operation of the flow control valve. First, we'll see its operation at low RPM when the steering angle is constant. The fluid from the discharge side of the pump is sent out directly to the steering gearbox through a small opening called the orifice. As the flow volume of the fluid increases with an increase in engine RPM, the pressure in chamber A, which is partially obstructed by the orifice, also increases. This causes the flow control valve to overcome the tension of the spring and move to the left. This in turn opens the passage to the suction side of the pump, discharging the excess fluid and ensuring that the flow volume to the steering gearbox is kept constant. Now what happens when the steering wheel is turned? When this occurs, the pressure in the power cylinder increases, and the pressure in chambers B and A of the flow control valve goes up simultaneously. Since this would cause the flow control valve to move further to the left, a larger volume of fluid would be discharged to the suction side of the pump, and the flow volume to the steering gearbox would decrease. To prevent this, another route is also provided to allow pressure from chamber B to be transmitted to chamber C, which is at the left side of the flow control valve. So the pressure in chamber C increases at the same time as that in chamber B, and the flow control valve does not move. In this way, the flow volume of the fluid to the steering gearbox is kept constant, even if the pressure in chamber B changes. This is how the flow control valve prevents changes in engine RPM from influencing steering assist. Now, what happens if the steering wheel is turned all the way to the left or right and this position is maintained? If this happens, the hydraulic pressure in chamber B suddenly rises. This would increase the load on the engine and each part of the power steering system. So to prevent this, when the pressure in chamber C rises above a set pressure, a relief valve opens so that an excessive rise in pressure will not occur. Next, let's take a look at the construction and function of the control valve. Let's consider the most typical rotary-type control valve. The control valve is located in the steering gear box. It consists of the valve shaft and the rotary valve. These two components are connected to either end of a torsion bar. The valve shaft is secured at the top end of the torsion bar, and the rotary valve is secured at the bottom. When the steering wheel is turned, its rotation is transmitted to the valve shaft and the torsion bar, as well as to the rotary valve and the pinion gear. The cutaway model shows how the rotation is transmitted. If there were no resistance from the road, the valve shaft and the rotary valve would rotate integrally. However, since there actually will be resistance, we will simulate this resistance in this model by twisting the torsion bar. This will cause the valve shaft to rotate, changing its relationship with the rotary valve and causing the size of the gaps between the valve shaft and the rotary valve to change also. Seen from above, the cutaway model shows what these gaps look like as they become larger and smaller in size. These movements switch the hydraulic circuitry, causing the fluid to be channeled to one side of the power cylinder or the other, resulting in appropriate assistance. Changes in the size of the gaps are restricted by a stopper provided at the pinion. Also, because of this, even if assistance is not provided because the engine stops or the drive belt for the vane pump breaks, the driver can still steer the vehicle. In other words, it can be steered manually, because the valve shaft makes contact with the stopper and directly rotates the pinion when this occurs. Now, let's observe how hydraulic pressure is applied by switching it from one hydraulic circuit to another. When the steering wheel is in the straight-ahead position, the fluid returns directly to the reservoir, and the openings on each side of each gap are the same size. This allows an even flow of fluid to the left and right chambers of the power cylinder. This also eliminates any difference in pressure that may build up between the left and right sides of the power cylinder. When the steering wheel is turned to the left, the size of the gaps between the valve shaft and the rotary valve are changed, as has already been explained. When this happens, the fluid flows to the chamber in the left side of the power cylinder. The hydraulic pressure moves the piston in the cylinder to the right, resulting in assistance. If the steering wheel is stopped halfway, the torsion bar returns to its original position, because the rotary valve rotates in accordance with the movement of the piston. Then the gaps between the valve shaft and the rotary valve return to their original size. The hydraulic circuitry returns to the neutral position, and the piston stops moving. When the steering wheel is turned to the right, the fluid is fed to the chamber at the right side of the power cylinder, which moves the piston to the left and generates assistance. Also, the sizes of the gaps between the valve shaft and the rotary valve produced when the steering wheel is turned change in accordance with the effort used to turn the wheel. As we have seen, the amount that the valve opens changes depending on the amount of the twisting of the torsion bar, and the appropriate assistance is generated by the control valve, which controls the volume of fluid flowing into the power cylinder. At the same time, the torque generated by the twisting of the torsion bar is transmitted to the steering wheel, giving the driver feedback informing him of the steering reaction. In summary, then, the control valve generates appropriate assistance by changing the direction of the flow of power steering fluid and by controlling the flow volume of the fluid. So far, the basic construction and function of the power steering system has been explained. In a real automobile, however, various other mechanisms are added to improve steering feel. Steering effort varies with vehicle speed, and the required steering effort is less at higher speeds. From the driver's standpoint, the ideal would be for the steering assist to change in accordance with the vehicle's speed. For example, when the driver has to turn the vehicle sharply at a low speed, as when parking a car, the vehicle should be able to be steered with little steering effort. On the other hand, during high-speed driving, the steering wheel should be firm, yet responsive. In order to attain this goal, various systems are utilized so that the assistance will be provided in response to vehicle speed. Let's take a look at two typical systems: engine speed sensing power steering and vehicle speed sensing power steering. This graph was used during the explanation of the vane pump. It shows the relation between engine RPM and the flow volume of the power steering fluid. In engine speed sensing power steering, when the engine RPM increases, the flow volume of the fluid generated by the vane pump decreases, as shown in the graph. For this reason, the required steering effort is increased by reducing the assistance. Now let's take a look at the mechanism that reduces the flow volume. In engine speed sensing power steering, a control spool is added to the flow control valve of the vane pump. This is the control spool. Located between the control valve and the orifice, the control spool reduces the flow volume of the power steering fluid by closing off part of the orifice. When engine RPM is low, the hydraulic pressure from chamber A is applied to the control spool. Although this should be enough to move the control spool to the right, the spool cannot move because spring tension is too great, so the flow volume of the fluid does not decrease. This corresponds to the point shown here on this graph, which we saw earlier. As the engine speed increases, the hydraulic pressure in chamber A increases, so the control spool overcomes the tension of the spring and begins to move to the right. The pressure in chambers B and C decreases because the orifice is gradually closed. This creates a large difference in pressure between chamber A and chamber C. The flow control valve moves to the left due to this difference, and a lot of fluid is discharged, causing the flow volume of the fluid to the power cylinder to decrease. As the engine speed further increases, the control spool closes off more of the orifice. But even if the engine speed is further increased and the hydraulic pressure in chamber A also goes up, the flow volume of the fluid to the power cylinder is kept constant because a lot of fluid is discharged to the suction side of the vane pump. This corresponds to this point on the graph. This is how engine speed sensing power steering reduces the assistance given when engine RPM is high. This produces an agreeable steering feel by providing appropriate steering wheel response even during high-speed driving. In vehicle speed sensing power steering, Based on signals received from the vehicle speed sensor, the ECU controls the current to the solenoid valve in the steering gearbox in accordance with the vehicle's speed, thus controlling the steering effort. Now let's discuss one type of vehicle speed sensing power steering, the hydraulic reaction progressive type. The features of the hydraulic reaction progressive power steering system are as follows. A hydraulic reaction chamber is provided inside the control valve housing, and as the vehicle speed increases, hydraulic pressure makes the torsion bar more difficult to twist, with the result that the steering wheel becomes heavier. In this way, a torsion bar that is thinner than in an ordinary power steering system is used to reduce steering effort during low-speed driving. In the construction of a hydraulic reaction progressive power steering system, a solenoid valve, a flow dividing valve, and an orifice have been added to the previous power steering mechanism. As current from the ECU increases at low vehicle speeds, the opening of the solenoid valve also increases, decreasing the pressure in the hydraulic reaction chamber. The flow dividing valve channels the fluid from the vane pump to the hydraulic reaction chamber. This is the construction of the hydraulic reaction chamber inside the control valve housing. When the pressure in the chamber increases at higher speeds, the plunger uses that pressure to push the control valve shaft in the opposite direction from that in which the steering wheel was turned. This increases the steering effort. Now, let's see how hydraulic reaction progressive power steering operates. A passage leads to the hydraulic reaction chamber through the flow dividing valve, and a special circuit controls the flow of the fluid by means of the solenoid valve, which is located midway in the passage leading from the pump to the power cylinder. Since the solenoid valve is wide open at low vehicle speeds, the fluid that goes through the flow dividing valve returns directly to the reservoir via the solenoid valve without passing through the hydraulic reaction chamber. This allows the steering wheel to be turned with little effort because the hydraulic pressure does not react against it. In the medium to high speed range, the solenoid valve is gradually closed as the vehicle speed increases, so the pressure in the hydraulic reaction chamber rises because the fluid is flowing into the chamber. This makes for a heavier steering wheel. What will happen if the steering wheel is turned sharply in the medium to high speed range? In this case, the hydraulic pressure in the power cylinder will rise. The resulting high pressure will be transmitted to the hydraulic reaction chamber via the flow dividing valve and the orifice. This will cause the steering reaction, that is, the feedback to the driver, to increase in accordance with the operation of the steering wheel. When the steering wheel is turned further and the hydraulic pressure in the power cylinder reaches a predetermined value, the flow dividing valve moves downward and closes the passage to the hydraulic reaction chamber. When this occurs, access to the chamber is limited only to the orifice. Because the increase in pressure in the chamber is restrained in this way, steering effort does not increase to any great degree. This is how hydraulic reaction progressive power steering produces an agreeable steering feel by utilizing precise feedback control proportionate to the vehicle speed from the low to high speed ranges. In the on-vehicle inspection of the power steering system, we will concentrate on the hydraulic system because it greatly affects the steering assist provided. Now let's take a look at the points to be checked. First, check the tension of the drive belt, which drives the vane pump. Next, check the power steering fluid. With the engine idling, turn the steering wheel from lock to lock several times to boost the temperature of the fluid to about 80 degrees Celsius or 176 degrees Fahrenheit. This must be done because the level of the fluid changes depending on the temperature. Now stop the engine and check the level of the fluid. If there are any air bubbles in the fluid level will drop when the engine is running because the air will be compressed. So be sure to check the level again while running the engine and confirm that there is no difference. In the event that the power steering fluid is low, ATF Dexron or Dexron 2 should be used. Next, check the hydraulic pressure. Use this pressure gauge. First, disconnect the pressure line from the steering gear box. Then connect the inside of the pressure gauge to the pressure line and the outside to the steering gear box. Now, run the engine at idle. Close the pressure gauge valve and check the hydraulic pressure generated by the vane pump. During this check, make sure the valve is not kept closed for more than 10 seconds, because high pressure will be applied to the hydraulic circuitry and could damage it. If the hydraulic pressure is lower than the standard value, the vane pump is probably faulty. Next, open the pressure gauge valve all the way. Then run the engine at 1000 RPM and check the hydraulic pressure again. Do the same at 3000 RPM. The difference in pressure should be no greater than the specified value. If the difference in the hydraulic pressure is greater than specified, the flow control valve is probably faulty. Next, with the pressure gauge valve still open all the way, turn the steering wheel all the way to the right and check the hydraulic pressure. Then check the pressure again after turning it all the way to the left. If the pressure is lower than the standard value, it means that the control valve cannot control the hydraulic pressure properly, or that the steering gear box has an internal leak. By checking the hydraulic pressure in this way, you can determine whether there is a fault in the vane pump or in the steering gear box. Next, use a torque wrench to determine whether the required steering effort is appropriate. Turn the torque wrench a quarter of a turn counterclockwise and check the torque. Then a quarter of a turn clockwise and check the torque. When you do this, the results will differ depending on the coefficient of friction between the road surface and the tires. So steering effort should be checked on a flat paved surface using correct size tires inflated to the proper pressure. For more detailed check methods, including the standard value for the hydraulic pressure, refer to the repair manual for the appropriate vehicle model. We are sure you can now understand the mechanism of the power steering system, which produces the proper steering feel. We hope that the knowledge you have gained through this video will help you to serve your customers more effectively and efficiently.